Good morning to meet you again in another video. So let us here explore what is the use of solving particular problems in thermodynamics. Okay, so the technology has developed too far nowadays. So why do we uh, you do not we use the technologies to solve problem rather than stick on to old traditional methods like thermodynamics? Okay, so let us discuss. Just see these problems. So these are all solved using analytical relations. Analytical relations in the sense simple equations we use like first law of thermodynamics and equations for specific cases like constant volume pressure, constant pressure process like that, okay, etc. So we use the formula and directly substitute and solve. But do they give the right perfect answers compared to numerical methods or finite element finite volume methods? The answer is no. So what is the significance behind studying these solving these problems? Let us look into some equations, some equations from some textbook like PK Nog. Okay, PK Nog book. So here we see ideal gas equation derivation. Yes. So here we read that it has been established from experimental observations that the PVT behavior of gases at low pressure is closely given by the following relation. Yes, this is the relation. Yes. So here we see that experimental observation. Yes, it has been derived from the experimental observations. So these formulas usually how they frame in thermodynamics is by using the experimental observations. Okay, so how it is framed, how the equations are framed is known by studying the solving the traditional problems, just like I have shown to you. Yes, traditional problems like in first unit of thermodynamics or second unit of thermodynamics. So here we see set of problems. Okay, so these are all traditional way of solving problems. So how the experimental things from the experimental things formula derived is will be known only based studying the traditional subjects. Okay, then we go for computational fluid dynamics. So when we go for computational fluid dynamics or finite element or numerical method, we use the same formula. Yes, same formula we use and program it and then give it to the computer to solve. So this is the reason why we are still sticking on to traditional methods of understanding. Okay, so don't miss it out. So don't hesitate to learn thermodynamics. It is very important. So we will I told you the understanding of the units is very important. Yes, here when we say, let us see how this equation is derived. I discussed there are confusions may arise when you use this formula. Yes, the experimental observation generated formula is PV bar equal to R bar T. Yes, so where R is the universal gas constant, which is given by joule per mole Kelvin. This is also very important. You should understand here when you say mole Kelvin, per mole Kelvin, what it means. We will discuss it in another video. So solving some example case, taking some example problem cases, we can see what is the significance of per kilogram or per mole, what is it. Okay, so we divide by molecular weight nu. When you divide by molecular weight, the bar goes off. Yes, bar goes off and it becomes PV equal to R, RTS. So we understand why we can write PV bar equal to R bar T2 PV equal to RT. On which basis we can write? Because by dividing molecular weight, so we get the unit in, remove the mole. Okay, mole, because molecular weight is in terms of mole, yes. So that will be get removed when we divide, and we get it in meter cube per kilogram, and the gas constant also we get joule per kilogram Kelvin. Okay, so the next we have to eliminate, if you want to eliminate small v and put capital V here, so what we should do? We should do is, we should know what the relation between small v, capital V and n, because we substituted n. Okay, so if you write, you will know that is P V equal to RTS. So from this we get converted to P V equal to N R bar T. Yes. So here V equal to V by N. Yes. That is, this is total volume. This is small v. Yes. Small v. This is total volume. Okay, so when you substitute V equal to V by N here, we get RTS, nRT, N R bar T. Then we have to, if you want to eliminate this, what we should do? We will use the relation, that is molecular weight, N equal to nu R. Okay, so let us write P V equal to nu R, nu N equal to N into nu. Okay, so we can write N nu R bar R T. So here we see, when we talk of ideal gas equation, here we use different equations with different parameters added. For example, here PV equal to PV bar R bar equal to T. Here it is without bar. Here it is N added, R bar remains, and then here M added. So we should not get confused solving such using this equation. It is very important equation in thermodynamics. Yes, so let us see how we can use different forms. Okay, so let us write PV bar equal to R bar T. Yes, so for this is for joules per mole Kelvin of R bar, and meter cube per kilogram gram mole of V bar. Yes, this is V bar. So let us write PV equal to RT, removing the R bar or V bar. Removing R bar V bar means, that is, we remove the mole, we take convert the units into meter cube per kilogram and joules per kilogram mole. Yes, so we want to convert, again we want to convert this V to capital V. Yes, we know it is the relation between, we know V equal to capital V by N. So substitute in this equation, we get P V capital V equal to N R bar T, not this equation, okay. So V bar is equal to only V by N. Okay, it's not V equal to V, capital V by N. V bar equal to V by N, number of moles, because when we say remove, want to remove moles, we divide by number of moles. Okay, so we get N R bar T, R bar T. Then it is written PV equal to MR. How we got this? We know molecular weight mu N equal to M, or Mn equal to N. Instead of using mu, we can use M also. Okay, so this is how we got, that is Nm equal to M. Okay, Nm equal to M. Here we use nu ms, so we can write R bar equal to nu R. Okay, so this we can write PV equal to N nu R T. Yes, this is nothing but M. So we get PV equal to M R T. Okay, this is how we got the equation. So again we have to understand, this is when we say ideal gas, we have different equation. We understand that there are different equations, and perfect gas, when we talk of perfect gas, is ideal gas and perfect gas are same or different? Let us discuss this in the next video, or next we will discuss that. What is ideal gas and real gas? What is the difference between ideal gas and real gas? We will discuss next, and then we will in depth we will see how to per gram mole means what is it, what is the concept behind it. We will discuss later. Okay.